Hi, this is Cheyenne, and today I'm going to talk about a question related to torsion in composite sections. So let's see what the question's asking us to find. So we have a 25-meter long stepped circular shaft ABCDE subjected to 4 torques and is fixed to the wall at point A, right? And it says if the maximum torsional stress in the hollow bronze shaft in part AB is 100 megapascal, right? We have it like a bronze here, right? Again, like the properties are given. Determine the applied torque T at C, right? And basically what this means is basically just find the maximum T that can be applied based on the information that's given. Determine torsional stresses in steel and aluminum in parts A, B, and BC, okay? So basically find any maximum stress in any of the materials in these two portions, and determine if the shaft is safe, if the allowable rotation of point E is given like 0.01, okay? Okay, so let's go over the geometric properties. First of all, so these are the material properties. These are given. These are modulus rigidity of steel, bronze, and aluminum for this question. And we have, these are all circular shafts. So as you can see, we have a hollow aluminum shaft with a 100 millimeter outer diameter, and hollow bronze shaft with 70 millimeter outer diameter. What does it mean? It means that the inner diameter for the aluminum shaft was 70 as well, right? So that's basically what it means. And we have a solid steel shaft with 50 millimeter diameter, right? And again, the same applies because this bronze section is continued, right? So basically here, again, I have 70 millimeter diameter, outer diameter for bronze, and 50 millimeter inner diameter for bronze. And again, like the steel shaft is 50 millimeter in diameter. So let's start with the question. So let's start with our procedure. What is going to be our procedure? So the first step for us is to calculate the reaction total in terms of T and draw the torque diagram. Okay, draw the torque diagram. And the next step for us is to calculate all the geometrical properties, polar moment of inertia. Again, we're going to go over one by one what all of these mean. Write the appropriate compatibility equation and use the given information, in this case maximum torsional stress. Again, like identifying this information is very important. Basically, this is key to solving our problem. And find the rest of the torques based on the compatibility conditions and based on the equilibrium equation. Okay. Now, the first step for us, as you mentioned, is to calculate the reaction in terms of T and draw the torque diagram. So these are given like 50, T, 10, 10. But this TR, so we just assume a sign for this, either like in this direction or in the opposite direction, okay? So that we have a reaction in the wall, right? Now, how can we find it basically in terms of T? We can say, okay, I have TR plus 10 plus 10. All of them, you can say kind of like in the clockwise direction, is equal to 50 plus T, right? So TR is equal to, basically TR plus 10 is equal to 50 plus T. So from there we can find TR equal to T plus 30. Okay. And next, I have to have a positive convention for my torque diagram, right? If I want to draw my torque diagram, I have to say, okay, what is positive, what is negative? And again, it's completely arbitrary. It's, whatever you're comfortable with, it doesn't matter like which one's positive or negative, right? You just have to be consistent. And for the first step, we didn't really need a convention. It's just a matter of finding something, finding a value in terms of the other. Now for this one, this is our torque diagram. Now how can we start? We say, okay, TR is like in this direction. We assume our positive direction to be in this direction. And this is like really common, and this is the positive direction usually used in most of the books. And here, TR, is it positive? Yes, it's positive. And what's the value? T plus 30. Okay, let's just put T plus 30 here in the positive direction. And then I have negative 50. Now the question you might ask is, okay, minus 50, is it going to go down or is it going to stay up, or what's the deal? And the answer is, it doesn't matter at all at this stage, right? We're just dealing with values, right? The values are important. So we know that it's going to be T plus 30 minus 50, it's going to be T minus 20. That's all we need. It doesn't matter if T is like going to be positive, T is negative, this is positive, this is negative. It doesn't make any difference at all. We're going to basically I guess, like modify these kind of signs later, right? Once we find our t value, right? Once we find our t value, negative, positive, we'll deal with that. We'll see that later in the coming pages. And then t minus 20, you might say, okay, and after that I have t going downward. So what does it mean? It means that minus t. So t minus 20 minus t. What am I going to have? Minus 20. And then I have 10 upward and another 10 upward, right? So that's basically what my torque diagram is going to look like, okay? Now, let's basically, the second step is basically calculate all the geometrical values, right? And in this case, it's in polar moment of inertia, basically, right? So calculate the J for the steel, for the bronze, and for the aluminum in this section, right? So again, like the J is dependent on your cross section, right? Not the material or anything. But in this case, because my basically bronze section is continuous, like from C to A, my steel is continuous from E to A, and my aluminum is from B to A, you know, it's basically also the material as well, right? And now in this case, what is the formula for polar moment of inertia? Pi over 32 times the outer diameter to the power of 4 minus the inner diameter to the power of 4 for a hollow section. In this case, you get this value, right? Again, this is the aluminum, 100 millimeter outer diameter. And here, although the inner diameter is not given, I know the bronze shaft has 70 millimeter outer diameter. So that's the inner diameter for my aluminum. Basically, considering, of course, that the glue or whatever it's connecting these materials together is, you know, it doesn't have, the thickness is not negligible for the connecting material, okay? Now we have for bronze, we have pi over 32 times 70 to the power of 4 minus 50 to the power of 4. Why? This is my bronze section, outer diameter 70, inner diameter 50. Why? Because my steel shaft has a diameter of 50 millimeter, right? 70 to the power of 4 minus 50 to the power of 4, I'm going to end up with this value. Then I have my polar moment of inertia for steel. For a solid section, there's no inner diameter. Or in other words, my inner diameter is 0. So pi over 32 times 50 to the power of 4, I'm going to end up with this value. And please note that I am getting my values based on millimeter to the power of 4. Okay. Now, this is the values I'm going to go with, like millimeter to the power of 4. But obviously, you can basically find them in meter to the power of 4. And if you feel comfortable with Pascal and Newton and, you know, something like that, you know, you can obviously, you know, convert them. For converting to meter to the power of 4, just multiply it by 10 to the power of negative 12, right? Because why? Because milli is 10 to the power of negative 3. To the power of 4 is going to be 10 to the power of negative 12. So in this case, you would have 7.46 times 10 to the power of negative 6 meter to the power of 4. But, you know, I think you'll see that millimeter is like easier because everything we have is a millimeter, right? Yeah, everything is millimeter here. But we'll see. So here, write the compatibility equations. Now, since we're assuming no slip between the different materials, the rotation of point B with respect to A must be the same for all three materials, right? Meaning that for portion, this AB, right? I have this composite shaft. And I would say that, okay, I consider no slip between the materials, right? Otherwise, there's additional shear involved there, right? That basically my torsion formula would not be really applicable. Now, because I'm assuming something like that, I would say that, okay, the rotation of aluminum portion from point B to A is equal to the rotation of bronze portion from B to A and the rotation of steel portion from B to A. And you'll see, okay, how is that possible? I would say, okay, if I consider, let's say, for example, the rotation of aluminum is more than bronze, what does it mean? It means that one of them is slipping on the other. Basically, one of them are moving, right? It means that it's not a composite. It's not fully composite, right? It means that, for example, if you consider an arbitrary point, like here, it means that for the aluminum part, it moved here. For bronze, for example, it moved here. What does it mean? It means they are slipping. That's against my assumption, right? So here, that's the reason. So rotation of B with respect to A for aluminum, bronze, and steel are equal. What does it mean? It means that, because this is what we're talking about, right? What does it mean? What is theta? TL over JG. So in this case, I just eliminate, basically just canceled this L. Why? Because it's LAB, so it's the same thing. So just cancel it. I don't I'm not going to use them in my calculations, just simplifying my calculations. And then from here, I'm going to write TAL, TBR, TST. I'm going to write my J, right? This is again like J aluminum, J bronze, J steel, right? For each of these basically materials, right, that I have. For example, this portion aluminum, this portion bronze, this portion steel. Multiplied by G, the molecular rigidity for each one. And as you can see, I'm not converting anything. Why? Because this is just an equation, right? If the units are consistent, as long as my units are consistent, everything is going to be fine, right? I don't have to write this as 28 times 10 to the power of 9. Even if you write it, it's going to be, cancelled anyway, right? It's going to be cancelled anyway. So this is my equation. This is very important, right? Okay, very important. Now, can I find anything from here? No, I can't find anything. I have to know at least one of them to find the others, right? But this is a compatibility condition. Now, what is the condition that I'm going to use? If you remember, we had a condition, use the given information. In this case, maximum torsional stress in the hollow bronze shaft in part AB is 100 megapascal. So the question gives us information that in the hollow bronze shaft here in portion AB, my stress, my maximum stress is 100 megapascal. What does it mean? What is the formula? It's TC over J, right? The tau is equal to TC over J. What is C? The maximum distance from the center of my circle. Now, we're going to talk about that. So TBR is equal to this. Now, how can we get our values here? So this is the equation, I just substituted. So basically tau BR times J divided by C is TBR, right? Because I'm looking for TBR. Tau is given, right? Tau is 100 megapascal here, right? 100 megapascal, and megapascal we know is Newton per millimeter squared. Multiplied by. This is J. Okay, we know that as well, right? This is the J for the bronze section, right? Again, like this is for the bronze section because the information is about in the hollow bronze shaft in part AB is 100 megapascal here. Okay, here. Now, until here, everything is clear. But what about this? Because I'm talking about the maximum stress, right? Where is the most distance from the center of this bronze circle? Is it like I have my 50 millimeter, I have my 70 millimeter? What is the max? 70 millimeter, right? Always like at the edge, right? Just before the edge, you have your maximum stress. On the edge, of course, you have 0. For example, for aluminum here at the edge, it's 0. But just before the edge, like it's maximum. For bronze, just before the edge, maximum. For basically steel, just before the edge, maximum, right? For that material. So in this case, I'm going to put 70 divided by 2, right? Not 50 divided by 2, not 100 divided by 2. This has all to do with the bronze material, right? Here in the bronze material, I have 70 divided by 2. 70 divided by 2, right? It's basically the radius, maximum radius, right? Diameter divided by 2. So from here, what's going to be the unit of my torque? I'm using Newton and millimeter consistently everywhere. So my unit for torque is going to be Newton millimeter, right? I'm going to end up with basically 4.98 times 10 to the power 6 Newton millimeter, or 4.98 kilonewton meter, right? Just divide by 10 to the power 6. And that's it. This is my key information, if you remember, right? So here, if you remember from the previous page, I had this equation. Here, just instead of just the TBR that we had, just put 4.98. And you can easily find T aluminum and T steel, right? Like that. And of course, the units are consistent, right? That's why this is also kilonewton meter. This is also kilonewton meter. And again, just to emphasize this point, no need to convert any of the values in the equation below, since we're using the same units for the corresponding values, right? Kilonewton meter for torques, GPa for modular rigidity, and so on. Now, what does the question again ask us to find? The first question basically was to find T, right? Again, we had to extract information and find our torque for bronze, right? Because that was the key information that we were given in order to find the torque in material for aluminum, for steel, for bronze. We already knew it. And for portion AB, basically, if we add these together, right? Because what were those? Those were theta B with respect to A, right? What is theta B with respect to A? We had TAB, right? This was TAB. TAB bronze, TAB steel, TAB aluminum. If we add all of those torques together, what does it mean? This is basically the torque in this section, right? This torque in this section was basically divided into the torque in aluminum, Basically, the aluminum is taking part of the torque, the bronze is taking another part of the torque, and steel is taking another part of the torque. So if we add them together, we're going to end up with this value, right? That's basically what we're going to do. So TAB total is going to be TAL, TBR, TSD, AB, right? And we found all of these values, right? We already found all of these values in the previous page. So just add them together, 22.82. 22.82 will be the total torque, T plus 30. So that means that T is negative 7.18. So, interesting. So here I have my torque in this direction, but this is negative. So I consider this to be like going down. So basically what this means effectively just, it's 7.18 in this direction, right? Now I'm not going to use this, right? I'm not going to change all of my directions. Okay, you can obviously do that, but I'm just going to stick with my sign here, negative 7.18. Just stick with my sign here, again here. Again, it doesn't just make any difference. I'm just going to, be consistent with my torque diagram. Whatever I have in my torque diagram, just put the sign there, right? Negative 7.18. Negative 7.18, what am I going to end up with? Like 22 point something, 22.82. What about here? I'm going to have negative 27.18, right? I'm just putting T as negative. What about this? Negative 20, negative 10. That's it, right? Or you could just, again, put T as 7.18 upward, redraw the torque diagram from the start. Okay, same thing. Okay, here, this is, you see, like what we did? 22.82, negative 27.18, negative 20, negative 10. Right? There's just some magnitude difference in terms of how the torque diagram looks like. Now, the second question was to determine the maximum torsional stresses in a steel, aluminum, and bronze in parts A, B, and BC. First, bronze. Do we know that? Yeah, we do know that, right? For AB, for part AB, not for BC, but for part AB, we know the stress in bronze already, right? It's given in the question. It's 100 megapascal. So that's one. But let's start for part AB anyway, so we're going to find it. We already know that the TAB aluminum, TAB bronze, and TAB steel. We already know all of them. We found them. We found that what is the torque value that each material takes. So what is the formula for tau? T C over J. Torque taken by portion AB, basically aluminum in portion AB. What was it? This is the maximum radius. What is the maximum radius? 100 millimeter divided by 2, right here. 100 millimeter, this is for aluminum. Divided by J, that we already found like in the second page. And from here, we're going to end up with megapascal. Units are, again, very important. As you see, I just multiply by 10 to the power of 6 to end up with Newton millimeter. How? I had kilonewton meter at first. So just times 10 to the power of 3, I'm going to end up with Newton meter. Times another 10 to the power of 3, I'm going to end up with Newton millimeter. Okay. And, as you see, I'm just using consistent units, Newton and millimeter. And my tau is going to be in megapascal, right? Why? Because what is the stress? Is Newton per meter squared or millimeter squared. I know megapascal is Newton per millimeter squared. For bronze, you can obviously find it, right? Again, like TC over J, but it's 100 megapascal. That's just already given in the question, and we basically found our torques based on that, right? That was the key information. But obviously, if you find it, it's going to be 100 megapascal anyways. Just again, like put the values again. For steel, 3.29 times 10 to the power of 6. This is the, again, torque multiplied by 50 divided by 2. Again, like you see, that's 50 divided by 2, right? The maximum radius divided by the J value, 134.0 megapascal. So this is the maximum stress in each of the shafts, right? Each of the portions of the shafts for the steel, for bronze, for aluminum in portion AB. Now let's move to portion BC. The problem in portion BC is we have no idea how much torque is gone. For example, I know the total torque again. The same issue is in part AB, right? For part BC, I know the total torque was 27.18, but some of this goes to the bronze, some of this goes to the steel. Do I know like what the proportions? No. But again, I can use my compatibility, another compatibility condition. What is a compatibility condition? The fact that the rotation from point C to point B is going to be equal for both bronze and steel, right? Again, like the same argument, the fact that there's no slip between these two cross sections, right? Between the two materials. they rotate together. It's composite, right? That's what composite means. So it means that theta CB bronze is equal to theta CB steel. What's the equation? Again, TPC, again, like this is just TL JG over JG, TL over JG. L is already cancelled because they are over the same length. And this is the J for the bronze, J for the steel, G for the bronze, G for the steel. From here, I can write this basically equation here, this relationship. So, but basically I know the total torque, right? And the total torque is 27.18. So what I do, just say, okay, TBC steel from bronze is the total torque is 27.18. So just use this equation, right here. Just substitute this TCBR as a function of TBCST, right, for the steel. Just put it here. Now for the steel takes 10.82, bronze takes 16.36. Easy as that. And just based on these, do the same thing that we did in the previous page. Find the maximum stress. Again, the torque, maximum radius, J. Torque, maximum radius, J, right? So it's very important. Again, the units, pay attention to the units. And here we get like these two values, okay? Finally, what is the question asking us? It's asking us whether the shaft ABCD is safe if the allowable rotation of point E is 0.01 radians. Allowable rotation of point E here is 0.01. So what is the allowable rotation of point E? It's a rotation of E with respect to A, right, to the wall. So what is the theta EA? It's theta E with respect to D, D with respect to C, C with respect to B, B with respect to A, right? Again, why have we divided like to this many like portions? Because again, as you see, the torque diagram is changing, right? As long as the torque diagram is changing, or the material is changing, or the cross section is changing, we have to divide our rotation, right? Why? Because it's basically the rotation is the summation of the rotations of different portions. So now the point is obviously we have different materials, right? So basically for this portion, what is the rotation of this portion? It's based on the steel, so we have one steel material, is easy. Same thing for CD. But what about BC, for example? For portion BC, I know that the whole section rotates like for both bronze and steel in the same way. So I see, you know what, just the same, you know, I can use like theta CB bronze here or theta CB steel here. It makes no difference. But I would say, okay, just to simplify my calculations, just let me use theta steel, right? Because I can factor out and use it like, you know, along this, like the values that I get for this. The same thing for AB, right? I know my theta BA for aluminum is equal to bronze is equal to steel. I can use any of them. I can use aluminum, I can use bronze portion, because, you know, all of them have the same rotation. But, you know, I'll just, you know, use my steel because it's easier for myself, right? It's just, basically what I'm doing is just taking this steel shaft all the way, right? Just to simplify my calculation, right? Knowing that the rotations are the same for BA, for aluminum, bronze, and steel. For BC, it's equal for bronze and steel is the only thing we have here. So I would say, basically this is what we're talking about, right? I would take the steel, I would take the steel, right? Because it's the same thing. But of course, you can use, you know, bronze, aluminum, right? Or bronze again here for BC. What's the equation? Theta EA is 1 over JG times TILI, right? This is only true because I have, you know, one material, right? Because I'm dealing with one material, just J and G, take it out, right? Same cross section, same material. This is why we did that. But obviously you can take any of the materials that you want. In this case, I have, again, like this is the J for steel, G for steel, right? And in this case, I did convert to Pascal, right? Because it's radians and I don't want to, you know, it's much simpler to basically deal with Pascal, basically Newton meter, basically, you know. So what am I going to have? So again, like what is this? It's a TL over JG. JG, I just took it out, multiplied by sigma TILI. TILI, let's start from the right side. Here I have negative 10 times 10 to the power of 3 Newton, right? Because it's kilonewton, right? Negative 10 kilonewton meter. So it's going to be negative 10 times 10 to the power of 3. Basically Newton meter, right? Again, like a meter is missing here. So it's Newton meter times 5 meter, which is the length. Okay, length plus negative 20 kilonewton meter, or negative 20 times 10 to the power 3 newton meter, right? Again, a meter is missing here, times 5 meter, which is the length, plus. Now, in this case, you would say, okay, should I use 27.18? Why did I use 10.82? The reason is, if you remember, what am I trying to find? I'm taking theta BA steel, right? Theta BA steel, or theta CB steel. So for theta CB steel, what is the formula? Is T steel CB, right? But 27.18 is the total torque, right? It's so for some of them is some of the torque is taken by the bronze, some of it is taken by the steel. How much is taken by the bronze and how much is taken by the steel? We found it in the previous page, right? We found it in the previous page. 10.82 was taken by the steel. So you can't use 27.18 as total here, right? You can't use this, right? Because we're either using the bronze or we are using the steel, because we know they have the same rotation. So negative 10.82, because we're dealing with the steel in this case. We just chose to find it for basically write the steel portion here, right? Times 5 meters, again, the length is 5 meters. And this one, again, we have to take the steel portion for AB as well, right? Because that's what we decided to do. So 10 meters is the length, and this is 3.29 times 10 to the power 3, right? Positive 3.29 was the torque taken by steel in portion AB, okay? So, and basically that's it. So again, like, there's a Newton meter, of course. And from here, we're going to have the answer of 3.6 radians, which is much higher than the allowable, basically, rotation. So, of course, this shaft is not safe. You have to redesign, use a larger cross-section on the right side, redesign, basically, probably use the composite shaft all the way, and anything basically to reduce our rotation. And in some cases, our basically stresses were also high as well, so we have to take that into consideration as well. And that's it for this question. If you enjoyed the video, please like and comment down below, and subscribe for more content about problem solving in structural engineering. And I see you next time.